Welcome to the section of the course on regression analysis. This covers a different variant of supervised learning, where the variable of interest is not categorical, but quantitative. This section focuses on different modes of linear regression. I start by explaining what linear models do and how they are estimated using the oldest and simplest procedure, ordinary least squares. Next, I discuss how we can evaluate how well a model fits data using stats models. I move on to the Bayesian mode of linear model fitting, discussing Bayesian ridge regression. Next comes ridge regression, a means of regularized linear regression. This is followed by lasso regression, another regularized regression approach. Finally, I discuss spleen interpolation. This is technically not considered regression, but it's a useful topic with some similarities to regression. Let's start by discussing linear model basics. In this video, we look at the basics of regression, linear models in particular. That is, we will see the objectives of regression, what a linear model is, and how to evaluate the quality of a fit. We see estimation via ordinary least squares, commonly known as OLS. We see these methods in action trying to predict the price of homes in Boston. Classification and regression both attempt prediction, but predict variables of different natures. Classification predicts whether a data point belongs to one of finitely many classes, such as whether a viewer clicks an ad on a web page or not. Regression, though, predicts a value from a continuum, such as how much a customer will spend on a website. Linear models are regression models that multiply the value of each element with a weight and add the product to produce a prediction. Linear models almost always include an intercept term, and yours should as well. At first, linear models seem restrictive, but they are actually quite expressive. Polynomials and other functions are linear models. Here are examples of linear models. Nonlinear models do exist and are more difficult to handle. We evaluate regression models by their errors. We define an error as the difference between the predicted and actual values for data points in the dataset. The errors of all data points are combined to form the sum of squared errors. We want a linear model to minimize this quantity. The least squares procedure, in fact, does this for a dataset, finding the coefficients of the model that would minimize the sum of squared errors for the data it uses in the fit. We don't necessarily guarantee that future data has a smaller sum of squared errors, though. There are hyperparameters to consider with linear models, fit with OLS or otherwise. One is what features to include in the model. For example, should we use age, race, and sex when predicting people's incomes? The other hyperparameter would be possible transformations in the model. Should our model take some nonlinear functional form, like a quadratic function or with interaction terms? In this notebook, I'm going to demonstrate how we can obtain OLS fits using Scikit-Learn. The first thing I'm going to do is load in the Boston dataset. After I've loaded in this dataset, we're going to have a look at the objects that it contains. Here we see the first 5 rows of the dataset and the first 5 prices that we would need to predict. And we can split our dataset as we have before when we were working with data that could possibly take one of a finite number of values. Here are the first 5 rows of the training dataset for prices. We're going to go ahead and use all the features available to us for prediction in our linear model. Now, in general, this doesn't necessarily produce better models. There are some features that may introduce only noise and make prediction more difficult, not less. But we're going to go ahead and ignore that wrinkle for now. We're going to import the linear regression object from Scikit-Learn along with the mean squared error metric. This is the go-to metric to evaluate how well a model is predicting the target variable. So after we load these in, we can fit the model. And we can also see an individual prediction. So we have the per capita crime rate, the proportion of land zoned, and a number of other variables. We're just making up a possible value for this and seeing what the predicted price of the home would be. In this case, the predicted price would be 42. So once we have this prediction, we can go ahead and make predictions for every row in our training data. And this will be the array of predicted values. Once we have this one-dimensional array, we can then compute the mean squared error metric. If we were to take the square root of this metric, we can interpret the resulting number as the average amount of error. The average difference between the home's actual price and the price that was predicted by our model. Now I want to perform cross-validation just to see how well things are going. I'm going to use the cross-val score function instead of what we've been using before. This wraps up a lot of the cross-validation procedure into one nice function. So this code right here will give us all of the MSEs for the folds that it creates, and I want 10 folds. That's what this code means. And the average negative MSE is given here. The reason why it's giving a negative MSE is because ideally we want the mean squared error to be as small as possible. So if we make the negative MSE as large as possible, then we are achieving our goal. This is like saying we would like our accuracy in classification to be as high as possible. We would like our negative MSE to be as high as possible as well. So we just saw how well the model was doing on the training data. Here is how well the model does on the test data. And we can see this square root of this number. So it doesn't seem like it's making that much more of an error, although it looks like it may have overfit somewhat on our training data.